Thank you. I'd like to thank very much to the organizer for inviting me to give this talk. I am Hertfordshire, which is just down a few stops on the train line to London for you. I've been there for more than 10 years after spending many places, Japan, Germany, Australia, and ended up in the UK. So I am going to talk about the origin of elements and the evolution of in galaxies, which is quite complicated, as you can see already in this movie. The chemical enrichment already took place in satellite galaxies. Satellite galaxies? It's not working here properly, but anyway. Oops. Already in the satellite galaxies before they accrete on a massive galaxy in the center of this movie. So the heavy elements are produced in stars, by stars in galaxies, but they are distributed outside the galaxies by supernova-driven winds in this small area, or by AGN feedback as well at the end of these massive galaxies near the universe. The elements are produced based on the nuclear physics. Nuclei are made of neutrons and protons, and the stable ones are in this the black area, which almost 1-to-1 relation of the number of neutron number and proton number, but the relation tilt because of the Coulomb force. Nuclear synthesis proceeds quite easily from the proton hydrogen to nickel 56, which is one of the most stable nuclei in this diagram, which decays into iron later on. That's why we have abundance of iron. Heavier than that, more heavier elements should have more neutrons, and there are two processes. One is the slow neutron capture process, which occur on the time scale of beta decays. The other one is the rapid neutron capture processes, which can produce up to the most stable one, uranium and thorium. Carbon is the lightest metals in astronomy, which is not easy to form because this beryllium-8 is unstable. Oops, I should. Sorry, I'm not very good at this. Okay, good. So it was Fred Foyle who predicted there should be an excited state of carbon around the energy of beryllium and alpha particles. I have never been to Fred Hoyle, but just only managed to see the statue. And then the question is, carbon and heavier elements are produced in stars. Jocelyn is going to talk about this, I think, later on at the public talk. The question is, what types of stars? How much of the elements are produced when following the evolution of galaxies? I've been working on this with my colleague, namely Amanda Caracas and Maria Lugaro. So just to summarize the results in one of the figures which you are familiar with, the periodic table. So Big Bang nuclear synthesis produced only light elements. Hydrogen, helium, and lithium already produced, that's why black out. Low mass stars produce half of carbon and 75% of nitrogen, as well as a bit of the first peak of neutron capture elements, strontium and so on, most of barium and lead during asymptotic giant branch phase. Quark-class supernova, the blue area, are responsible for the production of most of the elements in this figure. Binaries are also very important. Particularly type 1a supernova produce the majority of these iron peak elements in red. And neutron star merger also to explain the heaviest element. However, surprisingly, the contribution of neutron star merger in magenta found to be very small in this analysis. So when I say quark-class supernova, I included various things. The standard one is this 1987A happened in Magellanic Cloud. Type 2 supernova, also more brighter one, type 1bc, also occur at the end of massive stars. Some were black hole forming In any case, the production of our process is very small. The club nebula is a rather rare one, which this is an explosion of oxygen and magnesium core. And it's known that they produce some of the neutron capture element, but it's rather weak, so not the heaviest neutron capture element. The third one is hypothetical, but in a simulation, a computer simulation, if people set a condition of magnetorotational supernova explosion, the jet-like explosion, this ejector is found to be very neutron-rich, and in some successful case, they can produce the element up to uranium. So this is very important. The last one is not even simulation, it's a cartoon, but a collapser. Some people say this accretion disk can be neutron-rich, the site for the process, but other people found this is not so neutron-rich, so this is still debated. This particular star of extremely metal-poor star, it's called David Young star, is very unusual. So they strongly support the co-production of all elements by magnetorotational rather energetic supernova, hypernova. So this star is very unusually have a clear detection of uranium and thorium, beautiful R process pattern in the middle, and unusually have a strong zinc and nitrogen enhancement. So explain this abundance pattern, the magnetorotational hypernova was supported. So after the publication of the periodic table, I got quite a lot of feedback, namely from the binary people, and then wrote another paper focusing on particular question. Can neutron star merger alone explain the R process enrichment in the Milky Way? So we go back to the detailed binary population synthesis. I think Jan is going to talk about more. Also, we looked at the detail of nuclear synthesis yield of various types of neutron star merger, neutron star, and neutron star black hole mergers. And I found that both can be high. And then in the most optimistic case, like cyan line, it's possible to explain the solar ratio with neutron star merger only. However, you see in the metal poor area still, the black line includes magnetorotational supernova. And to explain the very rapid production of neutron capture elements such as in europium, magnetorotational supernova, hypernova are still necessary. Having said that, the next version of the periodic table includes this most optimistic case for neutron star merger, which you find very different, particularly for the heavier elements here, that the contribution from neutron star merger found to be quite large. To do this, I reduced the contribution of magnetorotational supernova in order to match the observational data. That's why the blue area is decreased now. But this is not based on the self-consistent nuclear sensor yield yet. I'm working on that. But this is probably the max contribution of neutron star merger, but community is working toward quantify what is actually the contribution of neutron star merger relative to core collapse supernova. So I jumped onto the Milky Way side now. So the same nuclear synthesis yields are included more large scale of cosmological simulation, in this case zoom-in simulation, to explain the formation and elemental distribution in the Milky Way. As we heard in this morning, each star have a different history together with the galaxy history. So its chemical enrichment also take place very differently. The bulge component, central component formed by the assembly of small galaxies at very high redshift, beyond redshift 2, where disk glow inside out gradually. That's why we have metallicity radial gradient by now. So this is a metallicity map of the simulated galaxies. The red is more metal rich, so the bulge component have more metal rich on the average. And also the disk plane has a higher metallicity. There is a strong vertical and a radial gradient. This is a simulation, but if I put the Gaia observation, this looks pretty similar. They're also quantitatively quite similar. Gaia also shows very beautiful both radial and vertical gradient. I can do the same thing for elemental abundance. So next figure shows the oxygen to ion distribution, again, the same simulation. the oxygen to iron ratio is low on the disk plane entirely. So there is not so much radial gradient, but very strong vertical gradient. So oxygen to iron ratio becomes high in the halo, which we know, but can be naturally reproduced by simulation. Also in this simulation, the bar area has a blue area, so the low alpha bar triggers the star formation, which results in low alpha component of the bar. The Gaia, surprisingly, I expected to see beautiful map of metallicity from Gaia, but Gaia also can do elemental abundance as well. And again, it's pretty similar future it's seen now. The same quantity in a different coordinate. Now on x-axis, I'm plotting metallicity, which roughly scale to the time, but not exactly, because in this Milky Way simulation, things are very mixed up. On the y-axis, I'm taking the same quantity alpha to iron ratio. So at the beginning, only quark supernova produces oxygen mainly, so it stays plateau. The oxygen to iron ratio decreased by the delayed enrichment of type 1a supernova. Simulation keep finding this bimodal distribution. If you see some areas are high alpha and there is a gap and then low alpha component. And then later on also the large scale galactic archaeology surveys find similar bimodality in the Milky Way. So the next question is this bimodality universal? Is it only in our Milky Way? Or can we see somewhere else? The only place we can do for Milky Way type galaxy is the Andromeda galaxy M31. It's challenging because it's far away, but we tried this by using planetary nebulae because they are brighter. And I found that indeed, particularly in the inner region of Andromeda galaxy have similar alpha to iron bimodality. So we think it's a general feature during galaxy formation. On the other hand, JW still looked at this tiny area of this yellow square area, and they didn't find, it's rather outskirt, they didn't find bimodality. So this is still debated. And then Japan's Subaru telescope has a multi-object spectrograph now, and then we're gonna look at this M31 alpha to iron bimodality from next year. In the last couple of minutes, I'm going to more larger scale. The high redshift galaxies, the iron is very hard to measure. The available elements are carbon, nitrogen, oxygen from emission lines. So this is another well-known diagram, similar nitrogen to oxygen diagram. The same, the x-axis is metallicity, but the y-axis is now showing the ratio of nitrogen to oxygen. It shows increasing trend. We know this from observation of nearby stars, nearby H2 regions, also higher redshift than prime alpha systems. This increase caused by metallicity dependence of nitrogen yields both in supernova and Roma stars. At low metallicity, this value rather stays constant. In our simulation, we can do this constant evolution by inhomogeneous enrichment from AGB stars. Also, a Wolf-Rayet or rotating massive star can also do this in the case of more simple models. Anyway, the different color points are redshift, so we even said in this paper that this relation is universal. Galaxy evolve along this relation. However, if we had yesterday, Genesis 11 is located here. It's much higher than any other observation, and also we can see in the simulation. So the last minute, I'm going to explain how to explain this such a high nitrogen to oxygen ratio. This is a rather simple chemical evolution models now, but I can explain this very high nitrogen to oxygen ratio only with Wolf-Rayet stars from rotating massive stars. So it's rather a larger number, slightly larger number of Wolf-Rayet stars, but in that case, without changing IMF. Still, it's possible to do this. The reason is if I assume this rather bursty intermittent star formation shown on this diagram. So in the fiduciary model, the chemical enrichment took place redshift 16. It was primordial, of course, back then, but it's because of star formation. Time scale is quite short. It's enriched to subsolar very quickly. And then there is a secondary gas accretion, which dilutes the gas, so line go back to the left. And in brief moment, the second generation Wolf-Rayet stars enhance nitrogen. So that's the peak area. Before quark collapse supernova produce a bunch of oxygen. And then later on, this line decreases. With this model, the gap is not necessary, but burstiness is necessary. So in that case, it's possible to explain this nitrogen emitters. Again, Subaru is going to look at similar objects, bunch of them in near future. The last point I wanted to make is I don't see any sign of very massive stars, but running out of time. Thanks very much for listening.